Welcome to Mrs. Miller's notes for her pre-calculus class. These are the notes for section 8.2, day 1, entitled Graphs of Polar Equations. And we're going to spend 3 days on this section, and today we're going to start off with just some easy polar graphing. Now, when we're graphing a polar equation, remember that equation has all of the points that are going to, well, the graph has all the points that are going to satisfy that equation. So we need, instead of x and y, we need r and theta as our ordered pairs that we're going to be graphing. And there's a lot of shapes that we're going to see today that are pretty similar to what we've seen in algebra. So we'll be graphing circles and lines because they can be easily represented in polar and rectangular graphing, but there's all kinds of other more advanced, funky looking curves that you can only get, or you can best get, on a polar coordinate system. Okay, so this is how we compare the rectangular to the polar. Now you can still plot points in a rectangular system. You go over 4 and up 2, for example. And in our polar system, we would go to the radian measure, like pi over 4, and then we'd go a certain length, like 4. Okay, so we're going to be graphing on this type of a system now, the round polar system. And for example 1, we're going to start off with a nice circle, basically, is what this ends up being. So we're going to sketch the equation r equals 3. Now, we want to write the equation in rectangular coordinates. We don't have to, because once we better understand what these polar coordinates are and how to graph them, we can graph it just by looking at the polar equation. But we're still practicing going back and forth between rectangular and polar, so we're going to rewrite this equation in its rectangular representation as well. So we have r equals 3, and remember, I would have to have a sine or a cosine, or I'd have to have an r squared, because those are the 3 formulas that we've been using to substitute and convert back and forth between polar and rectangular. So if I could get an r squared in there, I could substitute x squared plus y squared in for the r squared. And the way to make this r into an r squared is to square both sides of this equation. So then I'll have r squared is 9, and r squared is going to be x squared plus y squared equals 9. Now, this equation here is the equation for a circle. Its center is going to be at 0, 0, and then its radius is going to be 3, because 3 is the square root of 9. Okay, so if we were to graph that on a rectangular system, we would start at 0, 0, we'd go up 3, down 3, left 3, right 3. And basically that's what we're going to do here on our polar system. We're going to start at the pole, and then we're going to do a segment that is 3 units long, 1, 2, 3, and we're going to rotate that segment all the way around the pole. So we end up getting a circle that has a radius of 3. So we're more familiar with seeing this equation in its rectangular form as a circle, but now that we're practicing the polar coordinates, we can see that r equals 3 really means you have a circle with a radius of 3. Okay, so there's the nice, pretty book picture. Okay, so let's try another example now. Again, this is an equation that's given to us in polar form, so we'll convert it. We're going to graph theta equals pi over 3. Now, it's actually probably easier to graph it in the theta equals pi over 3 version in that form, but we'll convert it. And if we're dealing with theta, our conversion is to basically change it into the tangent. Okay, so I'm going to take this original equation and I'm going to multiply both sides by tangent. So then tangent of pi over 3 is going to be the sine over cosine of pi over 3. So sine of pi over 3 and then cosine of pi over 3. Sine of pi over 3 is going to be square root 3 over 2. Cosine is going to be 1/2. And then if I multiply by the reciprocal, which is 2, I end up getting the square root of 3 over 1. Now remember, our tangent theta is equal to y over x. So my tangent theta value is the square root of 3 over 1, and that's equal to y over x then. So now if I take a look at this little part right here, I have a proportion, and I can get, now that I have the x and y in there, I can cross multiply. So I would have, oops, I wrote x over y, it's supposed to be y over x. Sorry. Okay, so y over x. There we go. So now when I cross multiply, I'll have y equals the square root of 3 times x, which is basically slope-intercept form. You could make a decimal for the square root of 3, the 1.71. So that means we would start at 0, start at our center, and we go up 1.71 and over 1, up 1.71 and over 1, and so on and so on and so on. So this is actually going to be a line. Now, the easiest way to graph it, though, it is to take a look at our polar system here. And remember, we've got a couple extra lines. This first line we don't really use. This second line is going to be the pi over 3 measurement. This next one is going to be the pi over 4, and then it's pi over 6, and then this other one we don't really use very often either. Then we have our axes again. Okay? Oops, and I have those backwards too. Gosh. Okay. Let's try this again. This is the pi over 6. This is the pi over 3. There we go. So if we were to graph theta equals pi over 3, I would just rotate around to pi over 3 and make my line. Now I have to extend that line into the other quadrant as well. So you're going to do it on both sides of your origin there. And if I was on a rectangular system, I would start at 0, 0, go up 1.71 and over 1, up 1.71 and over 1. If I laid them on top of each other, it would be the exact same line. So I think it's actually easier to graph it in the polar form for this one, especially since we have the polar graph. So in your homework, you're going to see a couple problems like that where it's just very basic equations. They want you to convert them from the polar into the rectangular and then graph them. But remember, you could really use either polar or rectangular to graph, depending on which one you think is easier to interpret. But let's do example 3 now. This is our last one, and we're going to talk about how we can just graph this in the polar system without having to convert it into the rectangular system. Now, our first example, we just had r equals a number. Now we have r equals 2 cosine theta. So this is a little bit more advanced, but we can still make a table of values and graph. And I'll show you how to do this in your calculator as well in a moment. But if we make a table of values, we need r and theta instead of x and y. And normally, we pick x values in our left column, plug them into our equation, and we solve for y and put them in the right column. But for our polar system, the ordered pair is going to be r theta. So it's going to be a little bit flip-flopped here as far as how we substitute in. We want to pick values for theta because theta is what's being substituted into the equation, and then we'll get the r value out. So we're actually going to work backwards, okay? And for these, I'm going to pick a lot of values to start with for this first one that we're doing. As we get into more and more of these, you won't have to pick as many values for theta, but for now, I just want to be thorough and show you what happens. Okay, so we're going to start at 0, and then we'll do every pi value that we normally section our unit circle into as we move around the unit circle, or as we move around the pole. So I've got 0, I've got pi over 6, pi over 4, pi over 3, pi over 2, and then I'm going to go into the second quadrant as well. So then we would have the next value would be 2 pi over 3. I'm going to run out of room here, so I'm going to extend my table. Then I would have 3 pi over 4, and then 5 pi over 6, and then pi. So let me just stop there for now. And I'm going to take these values and substitute them in one at a time to the equation. So I have 0, so that would be cosine of 0. Cosine of 0 is 1, and then I have to take that 1 times 2, so I get the 2. Pi over 6, the cosine of pi over 6 is going to be square root 3 over 2, and then I have to multiply that by 2, so I get the square root of 3, which is about 1.71. So we might have to do a little estimating here. Pi over 4, when I substitute that in and take the cosine of it, I'll get square root 2 over 2, and then I have to multiply that by 2, so I get the square root of 2, which is about 1.4. Pi over 3, I substitute that in. The cosine value of that is 1/2, times 2 is 1. Okay, good. Get a nice whole number there. Pi over 2, when I substitute that in, the cosine of pi over 2 is going to be 0, times 2 is 0. And then for 2 pi over 3, that cosine value is negative 1/2. So negative 1/2 times 2 is going to be negative 1. So notice now it's the opposite of what I had up here for pi over 3. 3 pi over 4, the cosine value of that is going to be negative square root 2 over 2. So when I multiply that by 2, I get negative square root 2. So opposite of what I had over here for negative pi over 4. 5 pi over 6, when I substitute that in and take the cosine of it, I'll get negative square root 3 over 2 times 2 times the 2 up front is going to be negative square root 3, which again, opposite of what I had over here. And then for pi, cosine of pi is negative 1 times 2 is going to be negative 2. So the opposite of what I started with. So you will see some patterns that repeat here when you're making your table of values. And that can be advantageous because that can help you complete your table of values faster. Or sometimes it's the same value, you're just changing it from positive to negative. Okay? So now I have to go through and I have to plot all of these. So I'm going to start with 2, 0. Now remember, this is 0 degrees, so I'm not moving off the axis at all. And I have a length of 2, so I'm going to start right there. Okay, pi over 6. Now remember, that was actually the second line here. We've got pi over 4, and then we've got pi over 3. Okay, so I've got pi over 6 now. I'm going to have a segment that is 1.71 units long. So you just kind of have to estimate. This is my first little ring. This is my second ring. So 1.7 might be right about there, perhaps. At pi over 4, I need a segment that is 1.4. So maybe right about there, close to the middle. At pi over 3, I need a segment that's 1 unit long. So notice I'm starting to curve here. I'll connect my points in a moment. At pi over 2, I have a segment that's 0 units long, so I stay on that pole. So now I've gone this way. So it looks like I have a semicircle, the top half of a circle. Okay, now remember when we have negative r values, that means that instead of going up one segment, okay, this would be the 2 pi over 3 right here. Instead of going up one segment, I'm going to go back in the opposite direction, one segment or 1 unit long. And then at 3 pi over 4, which would be my next line, instead of going up 1.41, I'm going to go back 1.4. So maybe right about there. And same thing for 5 pi over 6. Since I have a negative r value, I'm not going to go forward 1.71. I'm going to go back 1.71. So right about there. And then my last value is pi. So pi is over here on the axis. But instead of going over to the left 2, I have to go the opposite direction. So I have to go the right 2. And that's actually where I started with. So I've made a circle. Now it maybe looks a little funky just because we're doing this by hand and I'm estimating, so it maybe looks a little bit like an egg or a football, but ideally it's supposed to be a circle. Okay? Now this is going to happen anytime you have the sine or the cosine of theta, even if you multiply it by a number. So if you have r equals some number times cosine theta or some number times sine theta, you're going to get a circle. Okay? And the only thing that's going to change between cosine and sine is where that circle is positioned. If it's positioned along the traditional x-axis or the traditional y-axis. And then the numbers are basically, that number out front is kind of like a radius, how long it is. Okay? Now there is an example of sine in your book. So if you want to see a graph of sine theta, that's in your book. You can take a look at that. And before we walk away from here, I do want to talk about domain and range. The domain of this function, the stuff we were putting in for theta, we put any real number. Granted, they were radians, but it was still a real number. And the range that we got out are r values. The lowest we went was -2, and the biggest we went was +2. So that means our range was between -2 and 2. And then if you want to think of it in terms of a circle, okay, remember our radius is basically the absolute value of that number that's out in front. Okay, this A number here. So that would be the absolute value of 2, which is 2. And that's how long our, or how wide our circle was. Okay, it's actually kind of more of a diameter, I guess. But the circle is centered at 0, 0. Oh, well, it wouldn't really be centered at 0, 0, would it? It would be centered at 1, 0. Okay, and again, this isn't really a radius. This is more of like a diameter concept. Let me fix that too. Okay. So the diameter all the way across is 2, and it's kind of centered at 1, 0, and then you get your circle. Now, if you're going to try and put this into your calculator, oh, we'll talk about that in a moment. Okay, if you're going to try and put this into your calculator, you have to change a few of your settings. You can graph both rectangular and polar on your calculator, but you have to go to mode, and you have to arrow down until you get to this option here, where it says function, par, pol, sec. The POL stands for polar. So you have to be in polar mode. So arrow down and over and then hit enter so that that polar is selected. And then you have to go to format, which is above the zoom here. So do second format. and you want to make sure that your polar graphing coordinates are on. So right now rectangular is flashing, that's because where the cursor is, but arrow over and hit enter so that polar is selected. Sometimes it does it automatically when you change the mode. And then if you go to y equals, notice that they've changed from y equals to r equals. And if I do cosine and then hit the X button, now it types in a theta for me instead of an X. And if I go to my table of values, if I do second graph, it doesn't have X and Y, it has theta and R. Now notice the way we made the table of values is flip-flopped from what's in the calculator. Okay, so the calculator is not going to give you the radian values for theta. It's going to give you the numerical values. And it's going to give you decimals for R. So sometimes this can be helpful, sometimes it's not very helpful. Now if you want to graph it, it's best to graph it on a square system. So do zoom 5. And then of course you can zoom in if you'd like to as well. If you want the calculator to do that automatically, do zoom and then go to option, oh my goodness, didn't realize there were so many alphabetical options there. It's option 0. Whoops, oh, we went too far. Go back down. Okay, option 0 is zoom fit. So if you do that, it will zoom in automatically for you. Okay, but again, remember it's going to fit your screen, and your screen's rectangular. So this circle now is a little squished. It kind of looks like a little football sort of egg shape. Okay, so I think zoom 5 is the best one. Okay, even though it's small or sometimes small, it looks more circular that way. But do not rely on your calculator to make that table of values for you, because if you use the table of values from your calculator, you're going to get all kinds of decimals, and we want the radians. Now, when we're dealing with our graphs for sine and cosine, normally when you, like I said, if you have some number times the sine of theta or some number times the cosine of theta, they're going to get you a circle when you graph them. So the radius will be the absolute value of a, and then the center will be a and then pi over 2, or a and then 0. Okay. And there's a table in your book. Here it's in a couple different boxes, but it's on your book in page 552, and it has a lot of the common shapes that we're going to be graphing. So it talks about circles and spirals. So it talks about how you can just have r equals a number for a circle, or you can have your sine and your cosine. Notice that the cosine is going to be along the x-axis, the sine is going to be along the y-axis. Okay. Should make sense because cosine in an ordered pair, the x is the cosine, the y is the sine. Okay, so it's connected to that. You can also get a spiral. We also have some, not really exactly sure how to pronounce these, but you have these crazy shapes that have like this little loop on the inside of them. Okay, and then you have roses, which we're going to see a lot. This one has like 4 leaves or 4 petals on it. This one has 3. Okay, and they get more complex as the equation gets more complex. So we'll be graphing some of those as well, some of the more straightforward ones. And then you have these other ones that kind of look like little figure eights or infinity symbols. Okay, and depending on sine or cosine depends how they're rotated and positioned. Okay. So take a look at these shapes and maybe keep that page handy in your book. So that way, when you see an equation, you can make reference to this and say, oh, okay, it should look something like this by the time I'm done graphing. Okay, so this is your homework for tonight. It's pretty short, but doing these graphs is a little time consuming when we're first starting out. But make sure you make the graph, make your table of values with the r and the theta values. Show me those radian measurements. Don't give me decimals. Okay. And there's graph paper on the class website. There's also graph paper in the drawer in the classroom, or you can search for some polar coordinate graph paper if you'd like and print some off for yourself. But remember, the solutions are worked out in the binder in the classroom and on the class website. And if you have any questions, come on in and see me before school.